Welcome back to the deep dive. Whenever we talk about a term like memory corruption regarding computers, I feel like the immediate mental image for most people is just destruction.
Mm-hmm.
You
Yeah.
think of the blue screen of death, you think of an application freezing up, that spinning wheel of doom, and it's just game over.
Yeah, the machine just gave up. It's the digital equivalent of a car crash. The engine stops, smoke comes out, and you're just stuck. That's the common perception, for sure.
Exactly. But looking at the source material we have today, that feels like a really surface-level understanding.
Hmm.
If you actually dig in, memory corruption isn't just about breaking things. It's more about altering reality.
That is a much better way to frame it. It's not just vandalism. It's more like reprogramming the rules of the game while it's still running. I mean, if you crash the machine, honestly, as an attacker, you failed.
Right. You just caused a denial of service.
Exactly. But if you corrupt memory correctly,
Yeah.
you convince the machine that your version of reality, a reality where you have total control, is the correct one.
And that is exactly what we're going to unpack today. We're stepping away from the famous Stack Overflow that gets all the headlines.
Oh yeah, the movie version of hacking.
We are looking at its quieter, maybe even deadlier cousin, the heap overflow.
The heap is where the real chaos happens. It's dynamic. It's messy. And honestly, because Stack Overflows have been researched to death and have all these protections now, sophisticated attackers are looking at the heap.
So we have a really clear mission for this deep dive. We're not just talking theory. We are going to deconstruct a specific, very technical exploit found in a program called secret.exe.
Right.
We're going to walk through how an attacker moves from a simple overflow, literally just typing too much text into a box, to gaining full root access on a Linux system.
It's a classic example, almost a textbook case, really, of how one tiny slip-up in some C++ code can lead to a total system compromise. We'll be relying on the breakdown in heap overflow exploitation.md and the actual source code from secret.cpp.
Okay, so before we break secret.exe, we need to understand the battlefield. The source material talks about the landscape of memory. I think most people have heard of the stack, but the sources mention overflows can also happen in the heap, the data, and the BSS segments.
Sure. So think of the stack as like a very strict librarian. Everything is ordered, predictable. You put a book on top, you take it off the top. It handles local variables, things that are temporary.
First in, last out.
Right. But the heap is for dynamic memory. It's the free-for-all zone. When a program runs and says, hey, I need to store this user's photo, but I don't know how big it is yet, it asks the system for a chunk of memory from the heap.
So it's grabbed on the fly. It's not pre-allocated in some neat little row.
Exactly. It grows and shrinks. And then you have the data and BSS segments. Those are more static. They hold your global variables, things that need to be accessible from anywhere in the program.
Like configuration settings or, as we'll see, file pointers.
Precisely. And that's the core mechanism here. It's about geography. It's about what's sitting next to your data in memory. Imagine you have a buffer. It's just a reserved parking spot for data, say for a text note you're typing. In memory, right next to that parking spot, physically adjacent, there might be another spot reserved for something critical.
Like a pointer. Or a variable that says, is this user an admin?
Exactly. And because it's the heap or the data segment, there aren't always the same strict guardrails you'd find on the stack.
So if I write too much data into my buffer,
You spill over.
you just spill over into the neighbor's yard.
And if that neighbor is a variable that controls the program's flow, you have just overwritten it. You've changed the program's instructions without ever asking for permission.
See, that's the part I want to drill into. Even if the program itself is limited-like, secret.exe only lets me write text notes. How does spilling over give me control?
Because computers don't understand intent. They only understand data. So if a program uses a variable to decide where to save a file, and I overwrite that variable with the new address, the computer doesn't say, hey, that looks suspicious.
It just says, okay, the variable says go here now.
Exactly. If you know the layout of the memory, you can hijack the control flow completely.
Which brings us to our target, secret.exe. What does this utility actually do?
It's deceptively simple. According to the source, secret.exe just allows users on a system to write their own private notes. It takes whatever you type and appends it to a file at varsecrets.
Okay, innocent enough. I type a note, it saves it. Where's the danger?
The danger is in the privileges. The source notes highlight a critical configuration. Secret.exe is a situate root. program.
Situate root. We see this a lot in these deep dives. For anyone new to this, why is that a double-edged sword?
Well, normally when you run a program, it can only do what you are allowed to do. But sometimes a program needs to do something you can't, like writing to a protected folder.
So Situate is like a temporary promotion.
Exactly. When you run secret.exe for the duration of that program, the operating system treats you as if you are the root user, the system administrator.
I see. So I'm a peasant, but for 5 minutes, I get to wear the king's crown just to sign one specific document.
That's a perfect analogy, and the exploit is essentially tripping the peasant while he's wearing the crown and tricking him into signing a death warrant instead.
So the goal isn't to read the secrets in var secrets. That's not the prize.
No, that's small potatoes. The goal is to use that temporary root privilege to modify the system itself. The source notes identify a specific line in the secret.cpt file that handles writing the data. We're not going to steal data, we're going to weaponize the writing process.
Okay, so let's get into the attack vector. The notes call this overflowing buffer by corrupting data file. Walk us through the mechanics here.
This is where it gets really clever. In the code, there's a buffer for your note text. And somewhere nearby in memory, there's a pointer variable called secret file.
And secret file tells the program where to save the note.
Correct. By default, it points to var secrets. But because of the memory layout, if we type a note that's too long,
We overflow our buffer and we hit the secret file pointer.
you got it. We can overwrite that pointer with a new address. We can tell the program, actually, don't write to var secrets. Write to this file instead.
But you can't just guess that distance, right? I mean, you can't just mash the keyboard and hope you hit it.
No, this is computer science, not jazz. You need precision. You have to calculate the offset. You need to know exactly how many bytes of data sit between the start of your buffer and the start of that file pointer.
And the notes mention using GDB for this. That's the GNU debugger.
That's right. So you run the program inside GDB, which lets you basically freeze time. You can pause the program, inspect memory addresses. You look up the address where secret file lives. Then you look up the address where your secret buffer starts.
And then it's just subtraction.
That is literal subtraction.
Yeah.
Address A minus address B. That difference gives you the exact number of bytes, the exact amount of junk text you need to type to fill that gap.
It's like measuring the distance to a bridge. You need exactly that many planks.
And once you cross that bridge, the very next characters you type will land right on top of that file pointer. You overwrite the destination.
Okay, so we've done the math. We know the offset. We can control where the program writes. And remember, the program is running as root, so we can overwrite any file on the system.
Any file. You have the keys to the castle.
So if you want to take over a system, what's the ultimate target? The sources are pointing to etc. password.
The classic etc. password is the master list of users on a Linux system. It defines who can log in, what their user ID is, what shell they get.
So if I can write to that, I can just add myself as a user.
You can add a new user, and more importantly, you can give that user administrator privileges. But you have to be careful. You can't just write, let me in. The file has a very, very strict format.
Right. If you break the format, you might just crash the whole login system. The source breaks it down for us. It's username, password, userid, groupid.
Some user info, the home folder, and finally, the default shell.
Okay, I want to pause on the password part. Usually in that second slot, you just see an X, right? Because the real passwords are in the shadow file.
Usually, yes. The X is a signpost that says, go look in, etc. shadow. But, and this is a legacy feature of Unix that goes way back, if you put a real hashed password right there in the etc. password file, the system will still accept it.
That is very convenient. So we don't even need to touch the shadow file.
Not at all. And the notes mention using the Python crypt module for this. You give it a password, say password 123, and it spits out the cryptographic hash string you need for the file.
So we have our payload. We have a string that says create user hacker 1 with this password and give him user ID 0, which is root. We inject that, overflow the buffer to point to etc. password, and hit enter.
In theory, yes. But there is a massive catch.
There's always a catch.
Always. And this is the real aha moment of this exploit. The program, secret.exe. It does something specific. Whatever file name it thinks it's writing to, it automatically attaches that file name to the end of the string you're writing.
Wait. So if I tell the program, hey, write this to etc. it opens that file, writes my fake user line, but then it sticks the text etc. at the very end of that line.
Exactly. And remember the format. The very last field in the user line is supposed to be the shell, usually bin bash.
Right. The program that gives you the command prompt.
But if your line ends with bin bashet's password because the program pasted the file name on the end, The system just looks at that and says, that's not a real file, invalid user.
So you can't log in.
You've corrupted the file, but you haven't given yourself access.
That is incredibly frustrating. The exploit works, you write the line, but the program's own clumsy logic just ruins it.
It ruins the syntax unless you use a workaround. And the one described in the source is absolutely brilliant. It uses soft links.
Soft links,
Yeah.
like a shortcut in Windows, basically. A file that just points to another file.
Exactly. A pointer on the file system. The attacker realizes, okay, I can't stop the program from appending the file name, so I need to make that file name part of a valid path.
Okay, how do you turn a file name into a shell?
Step 1. The attacker goes to a temporary folder, like Tampa. They create a soft link. They name the link Tempet password.
Wait, they name the link etc. password inside the template.
Yes, they're mimicking the path. And they make that link point to bin bash.
This shell.
This shell. Step 2, we go back to our exploit. We overwrite the secret file pointer to point to the real etc. pass.
Right, still targeting the master file.
But now we construct our malicious user string differently. When we get to the end where we define the shell, we don't type bin bash.
What do we type?
We craft the payload so that when the program appends the file name, the resulting path at the end of the line becomes tempet password.
Ah, I see. So the line written to the file literally ends with that path.
Yeah.
Tempet password.
The attacker manipulates the text so the garbage the program adds actually completes a valid file path.
So when the system tries to log you in later, it looks at that last field and says, okay, the shell is at tempet password.
It goes to that location,
And it finds our soft link.
which bounces it immediately to bin bash.
Yeah, boom, you have a command prompt.
It's so clever. It uses the file system's own redirection to fix the broken syntax.
It really is. It turns the program's flawed behavior appending the file name from a bug that kills the exploit into a feature that makes it work. It's like judo. You're using the opponent's momentum against them.
It is exactly like judo, and this is what separates a script kiddie from a real exploit developer. Seeing a roadblock and finding a way to use the OS's own features to bypass it.
So we have the plan. Now it's just about execution, and this is where that precision we talked about earlier comes back into play.
Right. The source notes emphasize this heavily. The value just before the file overwrite must be exactly 112 bytes long.
112 bytes. Why that specific number?
That's the distance we measured in GDD. If your payload is 111 bytes, you stop short and nothing happens. If you're 113 bytes, you overwrite the pointer with junk and the program crashes. You have to hit it exactly.
But our fake user entry, the HackerOne string with the hash, it's probably not going to be exactly 112 bytes naturally.
Unlikely. So you have to pad it. The notes mention you can play with the user information column.
It's the field that usually holds, like a full name or office number, right?
Yeah, it's just a text comment field. The system doesn't really care what's in it, so you can just add spaces or random letters like packing peanuts until your total payload length hits exactly 112 bytes.
So the final payload starts with HackerOne, the Python hash, UID0, GID0. Then a bunch of our packing peanuts in the user info field. Then root for the home folder. And finally, you set up the end of the string to catch that file name append.
Yes. You feed that into secret.exe. It overflows, hits the pointer, redirects the write to etc's bed, and saves the file.
And then?
Then you just open a terminal and type so HackerOne. You type in the password you generated. The system checks etc. password, sees the user, sees the UID is 0, which means root follows that soft link to the shell and grants you access.
You are now God on that machine.
You are root. And I love that the source note adds a little warning here. Make a backup copy of the file just in case.
Yeah, just in case you accidentally delete the entire user list of the operating system while trying to hack it. That's probably good advice.
It's a stark reminder that these exploits are destructive. If you mess up that etc. pass syntax, forget a colon, or get the padding wrong, nobody can log in. Not even the real admin. You've bricked the login.
So zooming out, we've gone from a simple note-saving program to total system domination. What's the big takeaway here?
I think it highlights that memory safety issues like heap overflows are not just about stability. They are about integrity.
Right. It's not about the program crashing.
No. We often think of hacking as guessing passwords or stealing keys. This is different. We use the program's own machinery against itself. We didn't steal a password. We injected a new reality where we have a password.
And we did it by understanding the landscape of memory and using tools like GDB to measure the distance.
And don't forget the creativity, that soft link trick. That shows that hacking isn't just about code. It's about understanding the entire ecosystem. The file system, permissions, legacy behavior.
It really makes you think about how fragile these systems can be. You trust them to follow rules, but if you can just nudge a pointer a few bytes to the right.
The rules change, and that brings up a fascinating point to consider. We exploited etc. pass, a simple text file. That mechanism is ancient. It's been around since the dawn of Unix.
We're talking 1970s concepts
Oh,
here.
exactly. So it makes you wonder, if a modern memory exploit can be used to manipulate such a fundamental ancient system behavior, what other legacy mechanics are hiding in our operating systems just waiting to be weaponized?
That is a terrifying thought. We're building modern skyscrapers on very, very old foundations.
And sometimes you just need to move one brick to bring it all down.
Well, on that cheerful note, that wraps up our deep dive into the heap overflow. Hopefully you'll look at your memory buffers a little differently now.
Keep your pointers safe, everyone.
See you next time.